related to the homework I posted? You don't want to tell me? All right. So we're going to continue our discussion of flow in a vertical tube today. So let's just get reminded where we left off last time. And I think last time I was writing here. All right. So just a quick reminder where we were. We are now going to employ shell balances to solve a problem in a tube, cylindrical tube, and that is sort of a quintessential problem that you're going to be solving in any kind of modeling of flow. Whether you're actually introduced, if you remember that introduction I had at the very beginning, I had visualizations of pipes on all possible scales in petroleum engineering. So you might have pipes in a very small pore spaces of a porous medium. Essentially, you can model that as fluid going through small pipes. They're interconnected. They're a network of pipes, you can say, within a rock. Those are on micron scale, or even on smaller scale, depending on the rock. Then you can move on close to the wellbore itself is actually an annulus, so it's a part of a pipe. And then you can actually have piping in any kind of system that is going away from the wellbore and delivery systems for oil. So pipes go on all kinds of scales. Now we're going to solve for steady state laminar flow of a Newtonian fluid in cylindrical tube, and by definition the pipes that we're solving for right now are relatively small because they're ensuring that fluid flow is actually laminar. So larger the pipe, larger the velocity through it, so basically you're going to have, or a flux through it will be larger, and that will actually cause some turbulence. So this analysis here is not applicable for very large pipes. So we always have to be aware of the physical context that we're solving for. Second thing is, it's a very good question whether the fluid we're solving for is Newtonian. Okay? Oil is considered to be Newtonian as long as I don't have all kinds of other stuff that might come with. Okay? So even when we have non-Newtonian fluids, sometimes we will approximate them with very viscous Newtonian fluids. That's one possibility. Water itself is very much Newtonian. It's what we think of when we think of a Newtonian fluid. However, if that water is carrying, if it's actually a drilling fluid, and it's carrying a lot of particulates with it, then it's actually bridging, sometimes possibly bridging into a non-Newtonian fluid. So you have to be aware of what is the fluid that you're dealing with. Nevertheless, this is one of the simplest cases that you will always go back to, and it's always, even if you're solving something for a complex non-Newtonian fluid where this analysis doesn't apply, you will still compare to this case. Okay? So it's sort of a baseline case for everything else that follows. So let's look at the setup we have. We have a tube. Where's my mouse? Hello. Whoa, hi. What happened? Okay. I got so excited about it that I moved it out of the... I'm looking for a mouse, but I don't. Do you see a mouse moving? There we go. All right. So this is a tube of radius r. I'm flowing in z direction, so it's my vertical component is z. I will have to work in cylindrical coordinate systems, so I have r, theta, and z. Theta is going in this direction. And I have tube of length L, and I have pressure P0 and PL that is actually driving this flow. Now, first assumption that we're making is that the only velocity that I actually have is Vz, so in z direction, and that velocity depends really only on r, or my distance from the tube center, or solid walls, however you want to look at it. Now, V theta would be this rotational velocity. Since there's no driving force to change it, I will not have V theta velocity. And similar for flow in radial direction, again, I would need a driving force or a gradient of pressure in radial direction for this flow to happen. So I'm going to have only Vz as velocity. Now, to actually apply shell balances, which is what we're doing, we're balancing momentum over a small fluid shell, I have to actually envision a shell in a cylindrical coordinate system. So here is one such shell. It's delta z thick in this z direction, and is delta r thick in r direction. So it starts from r to some r plus delta r in terms of radius. Okay. So one thing that we will have when we're balancing momentum, we know what our expressions for momentum are. We will be using combined momentum tensor, but for that we also need areas that this tensor is acting on. Okay? So first thing first, let's quantify areas. We have AZ, which is my both AZ and AZ plus delta Z. This is this blue area on top. Is blue actually properly visible? Do you see a difference between blue and... Okay. So it's not the super visible difference, but it's there anyway. So basically I have this difference between these two circles in areas, and that's my AZ. I can simplify it as 2rp delta r, because this term for small r is a second order in something very small. So to the first order approximation, I'm going to disregard it. So that is, I come in through this area and come out. And what we said is, okay, so this is area that is orthogonal to z direction, and I'm balancing z momentum. Okay? So basically I'm going to write down that phi z, which is z momentum transfer in z direction, okay, evaluated at z, times this associated area. That's sort of what comes in from on the top, okay? And then what comes out, and comes in, comes out is relative to just this coordinate system, really. I don't know whether it's coming in or coming out until I actually evaluate phi z, okay? But I'm just thinking about it as coming in and coming out because that's the orientation in the coordinate system. So it's coming out minus phi z evaluated at c plus delta z, so that's at the bottom, again, times the area. Okay? So that is the momentum transfer across these z-planes. Okay? Then when I actually look at the areas in r direction, the area at r versus the area at r plus delta r are two different areas. Okay? And they're actually, so I have this perimeter times delta z as their area. So that's basically this area on the side of a cylinder. So basically my area at r is delta z times 2rp, but my area at r plus delta r is delta z times 2r plus delta r times b. Okay? So those are two different areas, and that often causes a little bit of issue in solving the problems. So I will look at my z momentum transfer across r plane, which is phi rz. Okay? So z momentum transfer across r plane. And first, what's coming in through r is times the associated area AR minus phi rz evaluated at r plus delta r times the area associated on the outside, which is r plus delta r. Again, so this is stuff that is coming in and out orthogonal to those areas. Okay? So this is essentially our momentum balance. What would happen if I actually had phi theta z? I don't have area, I don't have a theta plane here in my shell. Okay? I would have to cut this to actually have a theta plane. Okay? But if I had a theta plane, let's say that I actually have, I'm cutting this donut, okay? So I cut a piece for a friend of mine and I create a theta area, okay? What would I add to this balance? phi theta z, and basically the same as here. It would be plus phi theta z evaluated at theta times a theta minus phi theta z evaluated at theta plus delta theta, because I'm cutting pieces, right? I have theta and theta plus delta theta. So across of this was a wedge that I cut off for a friend of mine, okay? Then, I'm a nice friend, I guess, then times the area a theta plus delta theta. So that would be added to this, okay? To actually have a complete description of theta, of my z momentum. This is all still z momentum balance. So if I create more area, then I have to incorporate it here. But I don't have more than 3 because I have 3 coordinate surfaces, okay? So basically this would be my balance, that would complete the balance, and then I still have to add the external body force, which is Az delta Z is the volume of this element times rho G. That gives me basically mass times gravity, okay? All right, so let's now actually continue from here. I will need another page. Okay. So what happens? Now, I will actually divide my entire, the equation that I had before. I will divide by volume. Which was Az delta Z. And if you remember, what was Az? Do you remember? 2pr delta r delta Z. So then what I actually had was minus phi zz evaluated at z and z plus delta z times that area Az, right? Which was essentially this. So I can just simply, since it was times Az divided by Az delta Z, it's just delta Z. This notation again, this notation means phi zz. So this term here is phi zz evaluated at Z plus delta Z minus phi zz evaluated at Z, and then I have a minus sign in front of it. So again, phi zz was just multiplied by Az when I divide by Az delta Z. It's easy stuff. Now, the other term is a little more complex, so I'm actually going to just write the details first before we... So it was phi rz evaluated at R, 2pr delta Z, minus phi rz evaluated at R plus delta R, 2p r plus delta r delta Z, and all of that is divided by 2p r delta Z. And then plus the last term is just plus rho G is equal to 0. Now let's look at this term. Easy stuff I can simply take out. Yes?
The first term, is there an R multiplied by that?
It's right here. Is that the term?
I mean on the first term of the equation. The first fraction.
This one? So there was AZ,
Correct.
and I just divided,
Oh, okay.
right?
Oh, you already divided.
Yeah, I already divided that one because that's the easy one. Now here, one thing that I have to be careful is that I have this function here.
So I have phi rz evaluated at r times r, okay? And I also have phi rz evaluated at r plus delta r times r plus delta r. So the problem here is that I actually have a dependence on r for this function of area, okay? So I actually have to make this inside the function because I have a dependence on r. So when I do that, I'm just gonna write this one down. So it's actually phi rz times r evaluated at r and r plus delta r. Because my function, my area was a function of r as well. Minus, yes. This was just to check whether you're paying attention. And now I divide things by r delta r. Plus rho g is equal to z. So, of course, I'm actually tempted to divide things by r and delta r and try to cancel them. But since this term is actually, this top term is actually depending, it's a function of different r, I can't necessarily do that. So I have to be careful about that. Or I can, well, I can, but then I'll get entangled into stuff I cannot get out from.
So we're basically putting the r inside the
Yeah.
del, right?
Because it is
Yeah,
a function of r, right? It's not independent, so I can't leave it outside.
Is that divided by r times delta r?
Yes. Okay, so now I actually go and take limits. I now do the shrinking of my shell to a point, and I'm going to take a limit as delta z and delta r go to 0. The first term is easy, so what will I get when I take the limit? Partial derivative, so it's dz dz. Nothing happens to r remains r, however it is that I'm shrinking, so it's minus 1 over r. And then what I have here is a derivative. I have a derivative, partial derivative of r times phi rz, okay? Nothing wrong with that. And rho g remains rho g. So this is our main partial differential equation. Okay? And this is the term 1 over r, partial r, r phi rz, is something that you're going to get in cylindrical coordinate system. It's compensating for the fact that my areas in r direction scale with r. So in spherical coordinate system, what do you expect to have? How do areas scale in spherical coordinate system with r? With r squared. So you're going to actually have an r squared in here. Okay? So expect that intuitively. And that's again because you're collecting over an area and that area scales with r or r squared depending on which coordinate system you're in. Or it doesn't scale at all. In Cartesian coordinate system, we didn't have this at all. Okay? Right, so this is the main partial differential equation that we're solving. Now it's time to actually resolve what all of these phis stand for. So I know that my tensor form for my combined momentum has pressure term, has viscous term, and it has convective term. Again, all of these are tensors. I'm interested in two elements of the tensor, of this tensor, phi zz and phi rz. Okay? So what is my phi zz? P plus tau zz plus rho vz squared. And my phi RZ, so I don't have pressure, plus rho VZ VR. And I know that I assume that VR is 0. So that is tau RZ. So let's plug these in. I will have minus partial z of phi zz, so it's dp dz minus d dz tau zz. Oh, actually, one more. Well, may as well write it in. Minus d dz of rho vz squared minus 1 over r partial r of time of r tau rz plus rho g is equal to 0. Does my vz depend on z? No, so I have some other stuff too. How about this term? The partial z, this term. How about this term? Same. What about it? So tau zz would be also depend on derivative in z direction, which I don't have that dependence. Okay. And again, taken once more, so however I take it, there's no dependence on z. So I will write this down as 1 over r partial r of r tau rz equals to minus dp dz plus rho g. So I will simplify my life a little further. We will define a function, generalized pressure or flow potential, which is P of z minus rho g. Z. So this term is then minus dp dz. And I'm going to call this flow potential. Also sometimes called generalized pressure. Don't remember it verbatim. So whether you have a plus or minus associated with rho g depends how is your coordinate system pointing with respect to your geometry. Okay. So here both g and main flow velocity are pointing in the same direction. So my z and g are aligned. Okay. If they're not, you're going to have a flip sign. So don't remember it, oh, flow potential is always P minus rho gz. Not always, it depends on your. So essentially look at the equation and see what's convenient. So define it, so this is minus dp dz. Okay, so let me now see. Did everybody write down before I change the page? So what I really have is minus 1 over r. Where did I pick up minus from? R or alpha is equal to minus dp dz. Now, technically, this here, since I'm assuming that my velocity is a function of r, the only velocity that I actually have in the system is a function of r, so does have to be this function as well, okay? So this is a function of r. P is actually this generalized pressure or flow potential is essentially a function of z. It's not a function of r, okay? So even if I have some z dependency, if I have any variable dependence here, it's actually a function of z at best, so to speak. So for these two to be actually equal, they have to be equal to a constant. So basically the first ODE that I can, this is actually not, it's not even a partial derivative, these are regular derivatives, so dp dz is equal to constant. So my generalized pressure or flow potential is a linear function of z. Okay, it's the simplest function I could have. And that's something that you're probably already familiar with, right? That my pressure is a linear function. So my dp dz, since it's a linear function, it's simply generalized pressure evaluated at my end minus the beginning of the tube divided by the tube length. Okay. Again, since p is my linear function. So what is my P of L? That is that pressure that I said that is actually given at the ends of the tube, my thermodynamic pressure P0 and PL were given, minus rho GL, and my P of 0 was simply P0. So I can call this PL and P0 if you'd like. Then the second thing to solve, and that's solved, I mean, those are things that are given as boundary conditions, and those are things that I can measure in the lab, so not a problem at all. Now we actually want to solve for first shear stress and then for velocity distribution. So this is equal to the same constant, which is minus dp dz, so it's P0 minus PL divided by L. Can multiply by R and integrate. So this is, I'm going to actually change this to, since the only dependence is on R, I can write this as a total or regular derivative. So my R tau RZ is when I multiply by R and integrate, it's going to be P0 minus PL divided by L. If I integrate R, integral is R squared over 2 plus some constant C1. So my tau RZ is P0 minus PL over L. R over 2 plus C1 over R. I need boundary conditions to actually solve this, or something that can help me get away. So I need to determine C1. Now this is a tube, and my R goes from 0 to capital R. As stated, is tau RZ defined at the center of the tube? It's infinity. Is that physical? Do I expect an infinite shear stress in the middle of a regular tube while having laminar flow at the same time? So it's not physical for us to have this term if I have flow in a tube. Okay? So at R equal to 0, tau R Z should not be infinite. So this is not even a boundary condition. This is really, is this realistic for this type of situation? So C1 should be equal to 0. Now, if I was actually solving for an annulus, can I do the same thing for an annulus? No, because R is equal to 0 is not part of my geometry, so who cares? I can have a very well-defined. So this is a general form of tau RZ in a cylindrical geometry. In this particular case, it doesn't make sense to have C1 not 0, but that doesn't mean that that's always the case. So don't just automate it in your brain. Okay? So for annulus, I will actually have to keep the form and find different boundary conditions.
R equals to something RA, you would have no slip at the end.
Right, so basically at 2 boundaries you will have no slip as opposed to just 1. So you're covered, you can actually still solve. So in an annulus you will have 2 solid surfaces that will give you boundary conditions. Not for tau necessarily, but for velocity profile. Okay? But in this particular case, we then have that tau RZ is P0 minus PL over L R2. And now, yes?
If R is 0, then tau RZ is 0.
If R is 0, yes. But it shouldn't be infinite.
Okay.
So it's okay to have, what is tau RZ? It's derivative of velocity. And I expect a parabolic profile. So that parabolic profile has a minimum or maximum, however you want to look at it, at that tip.
Yes.
So what's the derivative going to be?
Yes, no, my problem is if we put C1 0, then we will have tau RZ.
No. This remains the form. So if R is equal to 0, it evaluates to 0, and it maximizes an absolute value of the boundary. So what's wrong with having a 0 in the middle? So in the very middle of the tube, there's a 0 shear transfer. And it sort of makes sense because if it was non-zero, I would kind of have perpetuum. Okay. So I'm transporting things away from that point in terms of momentum. So I can have a 0, just a value of shear stress evaluated at one point that there's no problem with that. I cannot have an infinite value physically. I cannot support physically infinite value. So basically this is a linear profile. I get a 0 in the middle, and I maximize in absolute sense on the sides of my tube. Okay? And now I have to also find velocity.
Tau RZ should not be infinite.
Yeah.
Yeah, but
Or should not be. Oh my God. Sorry. I was like, what is the problem with it? Okay, not be. I didn't write not. That was the case. Is everybody clear what I wanted to say? So it should not be infinite. And I write should be. And I'm like, what is the problem with the statement? Oh, okay. Are we on the same page? All right. So this is tau RZ. And now I actually have to replace. So what is my tau RZ by definition? Can somebody look it up?
it's the Z momentum. Oh,
What is the formula in terms of velocity?
minus maybe
Is this correct? Based on Appendix B in your books? Double check. Learn to double check if you expect. This is something you would expect from Cartesian coordinate system. Doesn't necessarily have to be true. So is it true? So non-Cartesian coordinate system could have some weird 1 over r's thrown in there in the problem. Does it have it in this particular case? Either way, it might not make a difference since VR is equal to 0, but I believe it's Appendix B that has shear stress expressions. It's okay? What's left in either case is VZVR. So the point I'm making here is just because something is valid in Cartesian coordinate system, it doesn't just automatically translate to. So when I integrate this, my VZ of R is 1 over mu L. And I have 2 mu L, and then P0 minus PL. And I integrate R, so it's R squared over 2, plus some constant C2. And I need a boundary condition with, what is that going to be? So no slip boundary condition will give me C2. So my VZ of uppercase R is equal to 0. So when I plug that in, my C2 will be this, just evaluated at R square, uppercase R square, and positive. So altogether, are we ready? Can move on? Yeah? So my VZ of R is P0 minus PL divided by 4 mu L, uppercase R square minus R square, and this is my famous parabolic profile. Very, very often we are after, actually I'm going to put volumetric Q as uppercase Q. So this is my volumetric flux. And I have to integrate this profile. And I'm going to put R d theta. So this is integration in cylindrical coordinate system, which you will have to review. This is essentially area element, okay? Area element in cylindrical coordinate system, okay? So essentially, if you have something like this, and this is d theta, the area of this element is r d theta. Rings a bell? Somewhere. Take it from some place where you store that undergraduate calculus class that actually went over the integration in cylindrical coordinate system. Again, so area of this element is r dr d theta. That's cross-hatched. So that's why I have to actually have this r in there in integration. So when you do this integration, that part is now easy. You will get P0 minus PL over 8 mu L r to the 4p. And now average velocity is easy. It's q divided by the area, which is r squared p. So my average velocity over 8 mu L r squared. So this example is now the standard example that we're going to build off of. If I went, so I got the expressions for tau. So as I kind of integrated things in the shell balances, I got my equation. My equation in terms of phi, the one that is minus d phi zz dz, minus 1 over r d phi rz times r dr, plus rho g equals to 0, is for any kind of vertical case, okay? So that general equation is basically for any type of fluid, because until I actually show what phi is, I'm not specializing in any specific fluid. If I had actually an inclined tube, what would happen? I would have, rho g scaled by my angle. So it would be cosine this angle, okay? Beta or whatever I decide to call it. If I had a horizontal tube, what would I have?
I wouldn't have.
I wouldn't have rho g, okay? If I had, so then that's that general equation. Now that I started specializing it, I expressed my tau rz, and that most general form before I actually applied any boundary conditions is again good, maybe plus minus that modification of the outside body force, is basically good for any fluid. I still didn't say that it's a Newtonian fluid. Okay. Newtonian fluid comes into play when I'm actually solving for velocity profile. So technically that tau rz expression is actually valid for your toothpaste, which is not a Newtonian fluid. You have to squeeze to get it out. The moment you have to squeeze the fluid to get it out, it's not Newtonian. Okay? So it's actually a yield stress fluid. So basically the general form would be fine, and it would be fine in a cylinder, it would be fine in an annulus as well. Okay? So it's how I apply boundary conditions that actually specialize things further. And then this velocity is dependent on assumption that I have a Newtonian fluid, because I took the expression for tau that is for generalized Newton law. Okay? If I had a different expression for tau, which would also make things a little more different, because it wouldn't be just derivatives of velocity, but there might be dependence on velocity itself or its powers and so forth. Okay? Then it becomes much harder to integrate. But again, I can still pose the problem for any Newtonian fluid. So we have fundamentals for everything. Where we will go from here is we will actually go look at non-Newtonian fluids, and also what happens if I have a compressible fluid. So my rho is just not a simple rho, and I will have to massage the problem quite a bit to actually make it solvable. So there will be a lot of assumptions made to actually make things solvable. So that's our menu for the rest of the week.
Should I read something in particular for this meeting?
Are you done with everything that gave you?
No, not done. So should I read everything and then?
Yeah.
Okay, I'll do it.
Actually, I'll give you one that I'm reviewing.
Sure. Yeah, the one you told me.
Let's discuss that. Yeah.
And also, should I time myself when I'm writing the report?
No.
No.
No. Let me just exit here.
Oh,
Okay, and stop.